In this video, I'm going to introduce you to the RL circuit, so a circuit that has a resistor and an inductor. So I have drawn here a resistor where the resistance R, and we have an inductor here with an inductance L. So resistors look like these spiky things here. Inductors look more like coils, because they often are coils. They always kind of look like the binding of those like notebooks. And I'm going to start our circuit off here by, notice there's a power supply up here, and there's a switch here and a switch here. So I'm going to start this off by closing the switch there, so we're closing switch 1. And we're going to find that the current is going to grow at a rate that depends upon what the inductance in the inductor is. So we're going to apply Kirchhoff's rule to this scenario. So we have the EMF from our power supply, and then we're going to have a voltage drop across the resistor, and then we're going to have a voltage drop across the inductor. So we just close the switch, so t equals 0 seconds, and our current is going to equal 0 amps. If I rearrange the Kirchhoff's law to solve for the change in current with respect to time, and then plug in our initial additions such that the current is equal to 0, this term drops out because anything times 0 is 0, and we end up with the change in current with respect to time is related to the ratio of the EMF to the inductance. And what this tells us is that the larger the inductance is, the slower the circuit will reach the maximum current. Where at T max, I is going to equal the maximum current, so I max, and I max is going to equal the EMF over the resistance. And so that maximum current does not actually depend upon the inductance. It depends instead upon the resistance in the resistor. Alright, so we're going to return to Kirchhoff's law that we looked at before. And now I'm going to rearrange it into a form that is slightly more useful for what we want to do, because our goal is to be able to find the current in respect to time. So we need to actually be able to isolate the current and not have a dt or a di in there anywhere. So I'm going to rearrange it into a different form so that I can integrate. And I will leave this algebra exercise up to you if it particularly interests you. And now I'm going to integrate from 0 to I on this side, because we want to be able to find the current at some particular time in the future, and then from 0 to t, because we want to be able to find the current at that t. I'm now going to integrate. I'm using the same integral form that I used in order to do this for the RC circuit. So if you want to know where this answer to the integral comes from, please consult your notes from the RC circuit. And then applying log rules, I'm going to do the exponential raised to both sides and rearrange so that we get the relationship that the current is equal to the EMF over the resistance times 1 minus the exponential raised to the minus r over L times t. Alright, so inductors, or RL circuits specifically, have a time constant similar to an RC circuit, where your time constant this time is equal to L over R, so the inductance over the resistance. And once again, this is when 63.2% of the max current has been reached. Alright, so this is the formula we're using in order to find the current with respect to time as the circuit reaches the maximum current. What I want to do is take the derivative of this so we can look at how the rate of change of current behaves in the circuit as time progresses. And what this tells us is that as time progresses, so as t increases, this is actually an exponential decay term, so this is going to decrease. So as your circuit is moving towards reaching its maximum current, the rate at which it changes current actually decreases, or it slows down. So there is a slower and slower approach to that maximum current as time progresses. Alright, so we've returned to our circuit we had before, and technically speaking, at this moment, switch 1 is actually closed. We've allowed our current to grow to I max. Now we're going to open switch 1 and close switch 2, and we're going to bypass the power supply and allow the current to flow through here. So we're going to talk about current decay in the RL circuit now. So we're going to say the current through the circuit decays smoothly over time. So now when we go back to Kirchhoff's law, we end up with just the voltage across the resistor and the voltage across the inductor. Alright, so rearranging that, we can just add to the other side and then rearrange because I want to get current all on one side. And this you have to be careful of when you integrate because you're starting at I max and you're integrating to some I value. Here you're integrating from 0 to t. So before you had current growth, now you have current decay, and so the current behaves in the opposite direction. So when we integrate this, we end up with this. And then we can rearrange to solve for the current, and little I is the one that changes with time. And this allows us to calculate the current at any particular moment as the current is decaying.